Okay, we're gonna go on a little trip. Okay, I'm the driver, so I'm driving down the road this way, and I'm driving straight. You guys are in the back seat, so you're in the back seat of my car. We're cruising along, going just down the highway, and I'm gonna take a quick right. And as soon as I yank the car to the right, where do you go? Yeah, that's right. You get thrown to the left side of the car. I'm sure everyone has experienced that. Someone's driving down the road. If the driver takes a quick left, you feel like you get thrown to the right side of the car, or vice versa. What is that force? What force is throwing you against the side of the car? Or if the person keeps turning to the left, what force is jamming you up against the side of the car? That's a common misconception. That's a common question. And sometimes people refer to that as centrifugal or centrifugal force. Centra means center, and fugue means to flee, like a fugitive is running away. Centrifugal is running away from the center. So some people think that when I'm going around a turn, there is a centrifugal force pushing me to the outside of the turn or away from the center. That is a fictitious force. There's nothing squishing you against the side of the car. Then why, if the window was open, would you go flying out the car? What force is it? Well, it's actually not a force at all. It's your own inertia. Here's another Latin root for you. Inert means lazy. So inert gases are lazy. They don't want to do anything. Well, you and I are lazy. We don't want to do anything. Every every molecule, every atom in my body has mass. Another word for mass is lazy or inert or inertia, meaning that if I'm driving down the road in a straight line, every one of my atoms wants to keep that state of motion, wants to be going in a straight line. Now, when the car goes left, my atoms want to go right, and I'm going to get jammed up against the side of the car, not because something threw me there, but because my atoms were going 60 miles an hour in a straight line, and they will always go 60 miles an hour in a straight line unless acted upon. That's known as Newton's first law. You may have heard an object in motion tends to stay in motion, an object at rest tends to stay at rest. What that means, well, first of all, there's a little parentheses there, in a straight line. So what Newton was saying, 1687, I think, when he published that, he was saying, hey, guess what? I have this crazy idea that if you get something going, it'll go that direction at a constant velocity in a straight line forever. If you think about it, that's a pretty bonkers statement because no one has ever witnessed that happen, especially in 1687. No one had ever witnessed something go in a straight line forever. If you push a cart down the path, it'll go for a few seconds and come to a stop. If you slide something across your table, it'll go for a second and then stop. No one's ever seen anything just go off forever. Now that we have satellites and spacecraft, we can kind of get a better idea of that I can shoot something off into space and it'll go off forever. But Newton had never seen that. So that was a pretty profound observation or understanding of the universe, that an object in motion will tend to stay in motion forever in a straight line. So if that's true, how do you get something to go in a circle? Here's a really important understanding that I would like you to carry with you as you walk around the world, and that is, if you ever see something go in a circle, something is pushing on it, because things do not go in circles by themselves. So if I see something, let's for example, the moon go around the Earth, or the Earth go around around the sun, I'm watching an object go in a circle. Objects don't go in circles by themselves, they go in straight lines by themselves. So something is pushing or pulling on that object centripetally. Center seeking. Centripetal means center seeking. To pet means to seek. So if I am signing a petition, I am seeking something. If I'm in competition, I'm seeking something with or against someone else. Centripetal or centripetal means center seeking. That is a real force. Centrifugal is a perceived force. Centripetal is an actual force, and it's the force pulling something toward the center. Now, a little bit of detail before we get into the math. That's actually the only way I can push or pull on something without accelerating it. We've already talked about Newton's second law, F equals ma, or A equals F over m. In other words, if you apply some F, you're going to get some A to any m in the universe. So if I take any mass in the universe and apply a force to it, it'll accelerate. If my force is in the direction of travel, or even partially in the direction of travel, that will cause the object to speed up or slow down. And there's one exception. If I have an object going in a straight line and I push or pull on it at a right angle or orthogonal force, that will not speed it up or slow it down because no portion of my push or pull is in the direction of travel. It's only orthogonal. So what's that going to do? It's going to cause the object to turn. So if I have, let's imagine an object just flying through space in a straight line. If I push on it, give it a little tailwind, it'll speed up. A little headwind will slow it down. A little side wind will not change the velocity, but will cause it to turn. And that turn will be about the center that the force is pointing toward. And so if I'm cruising down the road and I get a sideways force, I'll actually turn I'll turn and not speed up or slow down. One more quick example of that, which I think is pretty neat. If you've ever seen a picture of an astronaut on the space station or floating out during EVA, extravehicular ambulation, they're floating around. They're these blissful guys just hanging out in space, floating through space. What's cool to think about is I've never been in space. I would think that would not be so blissful because the only way you can gently float through space when you're on the space station is to be going 17,000 miles an hour. So if you've ever seen like a picture of an astronaut floating out on a spacewalk, they're blasting through space at a mind-boggling speed of 17,000 miles an hour. Why 17,000 miles an hour? Because that's the speed that you need to be going sideways, that your own weight is just sufficient to keep you on an orbital path. So let me just explain that. So we all know, this is also one of Newton's laws, that any two objects attract each other gravitationally. Right now, you're being pulled down to the Earth. That's called your weight. And so if I'm an astronaut and I'm just a mere 200 miles above the surface of the Earth, which is how high they are, I'm falling like a rock toward the Earth. And if you just took an astronaut, put him right where the space station is and let him go, they would fall like a rock to the Earth. The only way you get them to miss the Earth is give them enough sideways velocity that as their weight pulls them down, their weight is orthogonal or at right angles to that velocity. Their weight just causes them to turn. And if they're going fast enough, they'll never get closer to the Earth. They'll just stay in orbit. Now, next class, we're going to derive the equation, but here's a little head start. That equation, we know that the equation, the force between two objects, between two masses, is gmm over r squared, or g, Newton's universal gravity constant, 6.67 times 10 to the negative 11th, I think, times the product of the masses of the two objects, divided by the radius squared, or the distance between them squared. That's the force pulling you down right now, and it's the force pulling the sun, pulling the Earth to the sun, and the sun to the Earth. It's a mutual force, and it's also like an astronaut in orbit. And that force would cause an astronaut to accelerate straight toward the center of the Earth. But if they have enough tangential or sideways velocity, if that force equals the necessary force to keep them in a circle, mv squared over r, their mass, times how fast they're going squared, divided by how far they are away from the planet, you can actually solve that for v, and you get about 17,000 miles an hour, and we'll do that next class. And that's how fast something needs to be going in a low Earth orbit. And so next time you see an astronaut like blissfully floating around, know that they're doing two things. One, they're falling like a rock toward the Earth, and two, they're blasting through space at 17,000 miles an hour. Like I said, we'll derive the math for that next class.